Well, it's time for an exploration of yet another piece of vintage Heathkit test equipment. And as usual for these videos, I'm going to start out by looking at Chuck Penson's excellent book, Heathkit Test Equipment Products. Going to the digital multimeter section. I've already done videos on essentially all of their digital multimeters. This chapter also has frequency counters in it, so I'm going to skip the frequency counter models. This was Heathkit's first digital multimeter, the IM-2212, which I have, but mine doesn't work. It's beyond fixing, and you can't buy any of the ICs for it, which is why it's beyond fixing. Just very obscure, weird, unobtainium parts. It does power up and the display lights up, and one of my earlier videos on Heathkit digital multimeters does show it powered up at least. So that came out in 1972. Digital multimeters were fairly new, at least in the price range where you could sell them to consumers instead of, very expensive units used by laboratories. Their next one was the IM-1212. Which was a much lower spec model. This was actually a fairly nice meter, really. Very good specs, very good build quality and everything. But kind of expensive. And so the IM-1212 was Heathkit's entry-level 2.5 digit, not even 3.5 digit. So the IM-102 was a 3.5 digit. Making them affordable meant going to the IM-1202's 2.5 digits, and then they milk that design with the change in form factor, but essentially the same circuit, the IM-1212, and then converted it to an LED display and a plastic case with the IM-1210. These are all essentially the same design, and I have a single video on these three meters, and that's the same one that touches on the IM-102. Then this guy made it into the 1980s as their low-cost entry-level hobbyist digital multimeter for all of $67.95. But in 1975, right around the time this was introduced, they had to have something that more serious people wanted. So they went to the IM-2212, which I've done a recent video on. That was a 3.5 digit unit with much better specs, better stability, better performance, all that good stuff. You could really use it for more than really casual measurements. Pretty nice meter really, but it's manual function, so you have to pick sort of a binary progression of these push buttons on the front and then select your ranges here. It's a lot of pushing buttons and a lot of rotating knobs. Not a real treat to use, but it does have a beautiful Panoplex illuminescent display, which is very appealing even today. People buy these things on eBay and just tear the displays out and throw the rest away just to get a Panoplex display that they can use in another project. Coming out a few years later, the IM-2212, which is the subject of this video, it was made for just a few years, 1979 through 1982. Substantially more expensive at just about $300. Pretty much a laboratory grade instrument, not as good as a hardcore professional lab would have, but pretty darn good specifications. And it says here the primary difference between the IM-2212 and other DMMs Heath was selling at the time, such as the IM-1210 and IM-2202, was that the 2212 was auto-ranging. That's, I think, the only one of all these meters that was auto-ranging. Nope. Yeah, this was manual ranging. These were certainly all manual ranging. This is an auto-ranging meter. It measures up to 1000 volts DC, 700 volts AC, 2000 milliamps or 2 amps AC and DC, and resistance up to 20 mega ohms. Basic accuracy is pretty good at plus or minus 0.2%. And you could buy an optional battery pack. An optional rechargeable battery pack costs an extra 40 bucks. And I described that in this video, even though I don't have that battery pack in the unit that I bought on eBay. Replaced by the IM-2260 and related series. And the IM-2260 was these guys, and I have a series of videos coming up. I have obtained the IM-2260, the IM-2262, and the IM-2264, and I also have the IM-2215 that I've done a separate video on. That's their handheld digital multimeter. One of them, they also had this guy, which I've not been able to find an example of. Anyway, so enough of this blather. Let's get on to the actual piece of equipment. So there's the glory shot. So just a quick look at the front panel. It is the model IM-2212. Has an LED display, plus there are two indicators when you're in ohms mode to indicate whether the value shown is in kilo ohms or mega ohms. Then you have your function selector switch, which starts with off, and if you have a battery installed, the battery charges when it's off. It can read up to 700, or it can take up to 700 volts AC, up to 2 amps if you're in current mode, and the common terminal can be as high as 500 volts maximum from earth ground. We have a function for DC volts, a function for AC volts, two functions for resistance, one which uses a lower interrogation voltage and one which uses higher. That can be useful depending on whether you're looking at semiconductors or not. I presume that the lower voltage will not forward bias a semiconductor junction, whereas the high voltage probably will. I think that's what that's about. Milliamps DC, milliamps AC, but again it can go up to 2 amps. And then if you have a battery installed, turning the function switch to that allows you to actually monitor the battery voltage instead of take a reading. And it's saying that you don't want to have a value of less than 7.20 minimum. Then there's a range hold. This is auto ranging. Normally you'd leave this in auto, but sometimes you want to force it to stay in a particular range, and then you can put it in hold. And then there's a zero potentiometer up here, which is for the meter in general. It's not for the ohms resistance mode, but it affects every range or every function. So this is just a look around inside the meter. There are 4 circuit boards. This large one on the side is the so-called input circuit board. It handles pretty much all the analog stuff. The AC to DC converter is that LM390, what is it? 356, an LM356 op amp. Some of the surrounding components are electronic switches. There's also a couple more op amps in here. Those are these cans there, although they're plugged into dip sockets. Those are the very front end op amps. I believe this big thing here is a precision resistor array, although the designations on the circuit board, it does say RN101 on there next to it. It's a little bit confusing how they have these designations in red. And interestingly enough, the manual does not have a circuit board diagram anywhere I can find. Heathkit usually had the so-called X-ray views, and I just don't find it anywhere. There's no page missing, it's just not there. So it's really hard to find things for troubleshooting. And I poked around in this and got it basically working. One of the ohms ranges doesn't work very well. All the other ones seem to work pretty well. This section here seems to be pretty much based on the, or affecting the very front end of the circuit. And then we have a sectioned off area for the second op amp. And then over here, this is again largely the AC to DC converter, but it also deals with the ranges. And this meter is kind of interesting because it doesn't have the usual big gang of resistors for all the different functions on a range switch. This is auto ranging, and it takes care of that logically by switching in either with transistors or with ICs, in some cases physical read relays and so on the circuit board. It engages the various elements through electronic switching. So you don't see a lot of the normal stuff. But as I demonstrated already, it does work, although it's a little iffy in the AC ranges, and like I said before, one of the ohms ranges just seems to be dead. Something's gone in there. This input circuit board is connected with 1, 2, 3 ribbon cables and 1 or 2 shielded cables to the main circuit board. You can see one ribbon cable snaking in down there, another one's down here, and another one's down underneath the function selector switch. The function selector switch is wired, with the exception of these few shielded cables here, the rest of it's all wired up to the front panel circuit board. So the main board seems to be mostly concerned with the auto ranging function. It has these 2 relays here, the big power transformer, and a couple more read relays down here. There's actually 3 of them there, kind of squeezed in there. The front panel board is mostly the display and the display drivers, but it also has some weird odds and ends on it. This is the power supply circuit board down here, and it has a little, not a switching power supply, but it has coming off the main transformer, which just generates it's a very simple transformer circuit, but the electronic circuit requires minus 12 volts, minus 7.5 volts, plus 5 volts, plus 7.5 volts, plus 12 volts, and another plus 5 volt, one for analog, one for digital. And those all have low power regulator chips on them, except for the a couple of them that don't need regulation. But there's a small transformer in there, and that is a transformer that's run by some transistors on that board. So they actually generate a higher frequency sine wave, or approximately a sine wave, that's then rectified by a bunch of diodes down in that area. And some of those have voltage regulators that are actually on the circuit board, although it's kind of hard to spot them because they don't look much like voltage regulators. They're the low power kind, which just look like normal plastic transistors. So you don't see the big ones with the heat sinks on them in here. All very interesting. There's only one filter cap. And then because the other circuits run at a higher frequency, they have very small filter caps, and that's what I think some of those little blue tantalum capacitors, or these down there, are essentially the filter caps. It's just because the circuit runs at a higher frequency than usual. In that sense, it's sort of a switching power supply, but it doesn't really operate as a switching power supply. It's a high frequency AC rectified to DC, and therefore the normal power supply conventions that we might be used to are not applicable here. Really, it's kind of a, for all the Heathkits I've torn into, this is probably the most adventuresome or adventurous power supply I've seen in pretty much any of them so far. Interesting approach. So let's see, we've covered the 4 circuit boards. This big area here can actually have an accessory on it. It's something you have to buy separately, and I don't have it on this one. It's a metal bracket that bolts down here and comes over here and then screws on to these two. If you'd bought the kit, there would be something that would attach to these 2 points and support it there. And that provides for the battery functionality. You can have this be battery operated. And there's a plastic plug in the back that you can kind of see right where the tip of my finger is. And if you had that accessory, then there would be a switch mounted there that would allow you to run this off of the line voltage or off of the battery. And the power switch on this does not switch the power to the transformer. This transformer is always powered if the power cord's plugged in, and I think that's because it's always charging the battery if the battery's in there. So again, a little different. These trim pots down here are all for the different resistance ranges. These are the transistor switches that switch one or another of these trim pots in for the different resistance ranges. There are also quite a few jumpers on this board which are moved around to different positions at different points in the calibration. Now, I recalibrated this unit because it was pretty far out when I received it, and the calibration instructions are quite involved, and I was just using I think there's 3 different ways of calibrating this, one using laboratory standards, one using some hodgepodge of other approaches, and one using internal references. And pretty much all the Heathkit meters had that option to just do it with internal references. If you were building this as your only meter, you wouldn't have another meter, for example, to calibrate this one with. So they always had some way of getting it working reasonably, with reasonably good accuracy, just using the internal references. Now this area here requires some shielding. It has to be off for calibration, but now I'm going to put it back on. Like that. Here's the rear panel of the meter. There's a fuse here. This is the line fuse for the incoming line voltage, and then this is a fuse for the milliamp input range. This plastic plug would be removed and replaced with some sort of a switch to switch between battery and line voltage operation if the battery was installed. And then here's the rather weird AC power socket. When I got this meter, I did not have a power cord for it, but I was able to find this old Belden cord on eBay. There was a seller out on the West Coast, I think Washington State, who had acquired a whole bunch of them from somewhere. And so that plugs in there. Unfortunately, this one has the cord going this way. It would be better if it came straight out or down or something, but that's what I could get my hands on. compared to most of the Heathkit meters, which usually just had some sort of a knurled screw that held the carrying handle and stand, this one has a fairly deluxe arrangement with a ratchet, or not a ratchet, but a set of detents in here, and then spring-loaded buttons to release them. Sort of like that. Okay, let's try the DC volts. I've got my power supply set to 1 volt. It's just sort of floating around here now because with the power supply output turned off, its leads are disconnected, so the test leads here are just picking up random electrical fields. Now I turned it on to 1 volt, and we're reading 0.997. The range is in auto. You can force it to hold in a range, but it is in auto range. So let's go to 2 volts, 3 volts, 4, 5, let's go right up to 9 volts, 10, let's go to 12, let's go to 18, let's go to 24 volts. Okay. I reversed the leads and it went to -24. Let's take it back down to say 15 volts. Should read -15. Let's go to -9 volts. And back down to say 2 volts. Right on the money. Okay, I have the meter in DC milliamps. I've got my power supply set for 24 volts. I have a 4 to 20 milliamp loop transmitter here, which will allow me to wiggle the milliamps between 4 and 20 milliamps to just get a basic test of the functionality. Right now it's set to about mid-range. Turn the power supply on, and it goes through its auto ranging and says 12 milliamps. If I throw the switch here, it should take it to 4 milliamps. Throw the switch back, it should go to 12. Throw the other switch, it should go to 20. Auto ranged, and it went to 20. You can hear relays click and things in there. That's part of the auto ranging circuitry. Throw the switch back, and I can adjust it all over the place. Okay, milliamps are working. Okay, I'm in AC volts mode, and I just have the inputs jumpered over to my AC line voltage disconnect box that I built. I have a separate video on that. And that is plugged into my Variac, which is set to minimum. I'll crank it up there. I'll turn this on. I don't expect to get a light yet because there's 0 volts. I've got my Variac set to about 100 volts, and I'm reading 95 there. Let me see if I can tweak it to say 100 volts. There. Take it down to about 50 volts. Take it up to about 120 volts. So that's working. I think it's basically, I forget which one it is. One of these 2 IC sockets is a little bit iffy. If I was actually going to use this for something, I might go in there and start spelunking, but it is working at the moment, so for the sake of demonstration, it's functional. Yeah, about 10 volts. Okay, the meter has a low voltage ohms range and a high voltage ohms range. I'm going to have it on high voltage just for the moment. I'm going to make sure the leads are shorted out. And it's sitting down there where it looks like it might need just a tad of tweaking. Yeah, there's a little residual resistance in the leads there, but let's just leave that alone. Hook it up to my resistance decade box, and let's crank in 1K. Just about right on the money. Let's make it 2K, 3K, 4K, 5K, 6K. I'll take it back to 3K, and I'll bring in the 100s and take it up to 4. So yeah, 3.34. It's close to 3.4K. I can bring it around. It's all working pretty good. Let's take it down to 30 ohms. Again, the accuracy, this is not great in the lower ranges. Let's go up to something higher. Let's go up to 50K. Really close. Let's make it 53K. Very close. Let's bring in 200K. So should be about 250, but it's switched to megs, so yeah, that's correct. Reasonably accurate. And let's see if it responds at all to the... Yeah, that should be about... Yeah, there's hardly any difference on that. So that should be about 20 ohms. It's a little bit off there. Just for yucks, I went to the low voltage ohms mode. What do I get now if I bring in 30 ohms? Yeah, 0.024K. That's 50, so it's working in that range too. But it does seem to be working pretty well. It could possibly use a little more tweaking in the calibration department, but it's doing pretty well. So I always try to include a little bit about the Heathkit manuals in these videos. This one will be no exception, but this particular meter, because of its complexity, actually has 2 manuals, and I was able to lay my hands on an original Heathkit manual for the assembly. It's a 2-part manual, the assembly and the operation manual. So this is the original assembly manual, and this is a reproduction of the operation manual produced by Manual Man. Manualman.com. And as usual with his manuals, they're very well produced. If I have a beef with it, I'll get to that in a moment, but let's just flip through the assembly manual really quickly. So it has the usual introduction, tools you need, introduction to components. It's divided into separate sections for each of the circuit boards, and then another section for chassis assembly and wiring. So it starts out with the input circuit board. It has a bill of materials for that, step-by-step assembly, the usual detailed, very direct, hard to screw up step-by-step instructions. Lots of good illustrations. Then the display circuit board. which has the big rotary switch for function selection attached to it. Shielded cable assembly, power supply circuit board, the main circuit board, all the same kind of stuff on each one. This has got the most parts, so it's the biggest section. And then another section on the chassis, as I said before, parts list, lots of diagrams for this. Goes on and on and on. There's even a transfer standard circuit board assembly that is a separate item, and this doesn't have its own bill of materials, so I'm not too sure about this one, if its parts were included in the chassis bill of material. I didn't really check, but I was kind of wondering how it just sort of jumps into the assembly of that part. Then there's the initial tests, operational tests. I'm flipping through several pages at a time here. A big table of troubleshooting. Then there's the calibration section. Course adjustments are just to get all the trim pots and trim caps into an approximately correct position to start off with. Mostly just set to the middle of their rotation, some to extreme counterclockwise, for example. And also the various jumpers that are used for calibration and testing are put in appropriate positions to start the calibration. Then there's the fine adjustment. This is the actual calibration. And as with all these things, you can use external standards. You can use a frequency counter to set the clock. You can use a beat frequency method. You can different ways of doing it. There's a temperature compensation section. There's a zeroing procedure, temperature compensation. You can use an environmental chamber. You can use a self-heating method, or you can just leave everything in the default adjustment positions and hope that it'll be reasonably good. Then there's the DC calibration with laboratory standards instructions, built-in standards instructions. AC calibration, same thing, laboratory standards, or transfer standards method, or built-in standards method. Ohm meter calibration, laboratory standards, built-in standards, and then final assembly, which deals with installing the battery pack if you have one and putting on the outer cabinet. That's the end of that manual. Then getting to the operation manual, a small beef that this happens almost every time somebody uses comb bindings. They use a binding too small for the size of the manual, and while it's theoretically page flippable, if anything gets a little bit out of sorts, they start binding up and you can start damaging the paper. This one is just barely big enough. It should have used the next size comb. So this starts out with specifications for all the different sections. It's pretty detailed. Heathkit wasn't slacking off in the preparation of their specifications. Then there's operation. This is how to use the unit. Everything from changing the fuses to using an optional RF probe. A lot of detail in here. Then there's the theory of operation. This doesn't call out any specific parts. It's more general, and it refers to the illustration manual and also to some fold-out pictorials in the back of this manual to help illustrate the general layout and operation. So there's several pages of this. We're still into the basic circuit theory. Then we get to the circuit description, which is down to the individual component levels, mentioning the specific resistors, diodes, transistors, capacitors, ICs, and what other parts there are. So it's quite detailed. You can go through this and have a ball. So this just goes on for a lot of pages. Then there's some troubleshooting. It's a more detailed troubleshooting. There's an example of where the pages start binding, unless you mess around with it to try to get everything lined up again. So Manual Man could have done a little better on that. So more troubleshooting charts. Semiconductor identification charts for all the semiconductors, telling you what their designation number is. For example, D1, D2, and so on. And then the Heathkit part number. But in this table, it's not identifying what the actual parts are. It's just correlating the circuit component numbers with the Heathkit part numbers. And I should point out that the prefix seems to be tied to the circuit boards. For example, all the part numbers with 100s should be on one board, 200s should be on another board. But you know, in the case of transistors, we're getting up into the 500s there. There's 4 circuit boards. So I haven't actually traced this out to see if they follow that religiously, but I did notice in the circuit theory section that there were a lot of mistakes, where they would mean, for example, U101 and they would write U201, that kind of thing. It drove me nuts when I was going through it, trying to figure out all the mistakes and what they actually meant to write. So they could have done more proofreading. Then there's an actual part number index where it identifies the Heathkit part numbers, and then the may be replaced by, it's the more generic part numbers that you could go out and buy. So we've got the displays, got all the transistors, several pages of various integrated circuits. And then we're into the pictorials, the illustration section of this manual. So, once again, more diagrams. There's a waveform and timing charts. More foldouts with the same kind of thing. Here's some simple block diagrams for use in the theory of operation section. This is the master diagram for the theory of operation. It's sort of a block diagram. Then we have the circuit X-ray views, circuit board X-ray views, transfer circuit board, power supply circuit board, display circuit board, input circuit board on a foldout. I wish these had been copied in color. It's a lot easier to see the foil and component side traces if they're in different colors. Once they're reproduced like this, yeah, it gets really hard to follow the foils at all. So diminished usability when reproduced in this fashion. But I suppose a color scanner and or a large format color laser printer weren't available. And there's the main circuit board X-ray view. Bunch of oscilloscope waveforms, and then there's the end of that. Then there's the large illustration book. Again, Heathkit just did so many drawings for their manuals. That's one place where I don't think anybody else did it nearly so well. They just took a lot of time making detailed drawings. A lot of, other kits have one diagram and then some text, but, you can't always picture what they're talking about. So lots of drawn to scale in many instances. Pictorials of parts to identify them. Diagram on how to cut up a sheet of insulation paper. All sorts of chassis assembly diagrams. Even have a diagram on how to twist the rear panel with the transformer on it around in a circle once to get a twist into the cables or the wires coming from the transformer. Instead of just saying do it, they illustrate it. That's why Heathkit manuals are the best, even when they make mistakes. These are the diagrams used to identify test points and adjustments for calibration. This one talks about installing the battery pack module. And that's the end of that. Okay, the part you've all been waiting for. The long-winded, detailed breakdown of the schematic and theory of operation. But compared to what I've done on most of my other Heathkit test equipment videos, there's just no way I'm going to spend 2 hours talking about this. It's pretty involved. So I'm going to try to go through and just sort of hit the highlights. So let's start out with the power supply. Pretty conventional transformer input. You can wire the transformer for 240 volts or 120 volts. The input, as I probably mentioned before, is not switched. Whenever the unit's plugged in, the transformer is always powered, it's always producing its secondary voltages. The battery circuit is not shown here because it's an accessory. There are 4 terminals coming off the main circuit board. One of them is circuit ground. This side comes off of one end of the secondary winding here. This one comes off the other side of the secondary winding. So there must be rectification on the battery charger charging circuit board. And then the output is coming off of the red terminal here, between there and ground. And that, if you have the switch on the back to select line or battery, then you can pick from the voltage coming from the battery, or you can pick from what's coming from this rectified and filtered DC voltage. Notice that there are different taps on the winding for the rectifier here, and that the voltage is a bit higher between the extremes than it is there, and that's there no doubt to get a higher battery charging voltage. This is a simple way of doing it. So your normal power supply for line operation is this full wave rectifier, center tapped, the single large electrolytic capacitor on the main circuit board, and then you would select line with the switch on the back of the meter to use that supply, or you put it in battery mode and select the voltage coming off of the presumably charged battery. If, however, you don't have the battery, then you don't have this switch here, nothing's plugged into this connector, and there's a solder blob jumper on the main circuit board that just bypasses this so that the voltage coming off of the filter capacitor here is always used. This is where the power switch comes in. This is one contact on the function switch on the front panel, which acts as the power switch, but it's always after this point. That's because whenever you're plugged in here, this secondary winding is always being used to charge the battery whenever it's plugged in. So you don't want to have the switch up here, you want to have the switch down here. So that's what this is. Then we tap off of this through this resistor, and this goes up to another contact on the function switch. When you're in the battery test mode, this is where it picks up the voltage. Now we go to the power supply circuit board. Oh yeah, one other thing. There's another winding, another secondary winding on the power transformer. One side just tied to ground, goes through a half-wave rectifier on the power supply board, and that just continues on here, goes down here, and it's used with this trim pot. Trying to hold the camera steady here. With this trim pot to pick up a AC reference voltage that's used for self-calibration. And the other side of that's always tied to this set of resistors that are primarily used for self-calibration or internal calibration standards for calibrating the ohms ranges. But this test point here needs to be connected to ground in order for this potentiometer to be used, and indeed during the ohm meter test or the voltage calibration steps, a jumper is placed from this test point to circuit ground, thereby making this point ground and thereby activating this circuit here. When you don't have this tied to ground, then this is available to measure between these test points to get different reference resistances from these precision pre-calibrated or pre-tested and measured resistors, the values of which are written on a label inside the meter. So also pulling off of this same half-wave rectified, and I should add non-filtered point, there's no filter capacitor there, you've got a Darlington transistor with a diode on the output going to this small capacitor and a resistor, and that provides a test point that's used for certain operations in testing, troubleshooting, and calibration. And this is turned on and off by a signal coming from the one of the two main AC to DC converter ICs. It's the so-called M/Z measure mode or zero mode. The ICs constantly run a cycle where they're either in measurement mode or auto zero mode, and that signal is used as a clock by this circuit here to turn this transistor on and off at the appropriate time in the master IC's cycle. And then that provides this test point here that's powered from here and sunk to ground or not. This is basically a pull-up resistor, and therefore you get a version of the clock signal which can be used here. Now the switched signal from the power switch, and that's again coming from either the battery or this rectifier and filter circuit here. This is the main power supply feed and the only one that's switched. Come onto the circuit board, there's a small filter cap, and it's basically used to just drive this circuit here. This pair of transistors are both connected it's sort of a mirror image to this primary winding on this toroid transformer, the center of which is grounded, and then they are in turn fed from this power feed. There is a little jumper there, which is normally in place, and their bases are fed from diodes coming from this other winding, which is shown here as a primary, but it's really a secondary, just shown on the primary side of the transformer. Its center tap is connected through this transistor and through a circuitous path down this way. I won't get into that right now. I may skip it altogether because it's fairly complicated. But if you presume this is grounded or something right now, or at least held to a voltage, then the signals, whether they're positive or negative on the flux of the transformer, are going to energize these two halves of the winding one way or the other, and through these diodes then they turn these transistors on and off. So basically one's conducting or the other one's conducting, and it's set up to oscillate. It's I think a not very rounded wave. It's pretty much a square wave. So what you get is a square wave oscillation here that's pushing and pulling on the flux of the transformer, and then the big secondary here taps off of that and uses it in several ways. I don't know what the frequency is here. I was looking for where it says, but certainly it's fairly fast. With a transformer as small as the one that's on there, and with the filter caps being really small, I've got to believe it's a fairly high frequency of oscillation. That just makes all these other components more efficient. You can have a smaller transformer, smaller filter capacitors, and so on. In that sense, it's like a more modern switching power supply. So we again have a center tap here on this secondary. So it's a big center tapped secondary. And way out at the extremes, we're connected up to a full wave bridge, half of which is shown here, half of which is shown here. And that provides the negative side of that bridge. Down here we have a small filter cap, and it goes through a 79L12. That's a low power 12 volt, negative 12 volt regulator, which produces the minus 12 volt source used by various analog circuitry, mostly the op amps, but other things as well. The positive side of that diode bridge is also filtered, and it goes to a 78L12, the low power version of the standard 7812 plus 12 volt regulator, and it's providing the plus 12 volt source to whichever analog loads need it. Now if we go a little bit inboard on the transformer from the center tap, the voltages will be lower, but otherwise it's the same. Here's half of a full wave bridge, here's the other half of the full wave bridge. The positive side has got a small filter cap, and this one does not have a voltage regulator. It just becomes an unregulated plus 7.5 volt source, and the negative side of it is similarly unregulated, providing approximately minus 7.5 volts for those circuits that need it. And then finally, up really close to the core, the center of the winding, is another full wave rectifier, but it's not a full wave bridge, with just these two diodes, a little bit bigger filter capacitor, another one of similar value over here, and this provides a non-regulated plus 5 volt supply just to power the LED display, because that takes a fair amount of current, so it has its own power supply here. And then finally, back from this same power feed, but bypassing the power supply circuit board, is the rectified voltage that goes through another 78L05. That's, well, I guess it's the only 78L05, not another one. And this is the low power version of the standard 7805 plus 5 volt regulator. Since it's a low power one, it's obviously not got much of a load on it. And this provides a plus 5 volt source to the logic ICs. Now, it is true that a lot of the ICs are actually LS ICs, like 74LS. So that's low power Schottky. So they're not all that power hungry. And there's also some CMOS 4000 series logic in here, which is, you know, CMOS, and it doesn't take much power. So they can get away with a fairly low power regulator for those logic circuits. So I think that covers the entire power supply section. It looks complicated, but it's really fairly simple, just repetitive. Alright, taking a look at the front end of the meter. These are the two terminals here. There's only the so-called input or in and the common terminals. That's all there are. Most of the other Heathkit meters from this period have at least 3 jacks. You have to move the leads around depending on what you're measuring. But this meter is pretty advanced. It's like a modern meter in that sense. It does most of the switching electronically instead of requiring the user to move things around. And you have a fairly simple function selector switch here. There are 4 gangs of it here, so 1, 2, 3, and 4. There's a couple other gangs elsewhere in this circuit, but these are the primary ones. If we follow the common one through here, it just sails through here, goes through a shielded cable, comes over here, and makes its way to both the digital ground and the analog ground on the circuit board. They're electrically the same, but for noise considerations, they're tied together. This appears to be where that's done. Which makes sense, because usually when you want to bring 2 parts of a circuit together, like 2 different versions of a ground, for example, you bring it together at a single point, otherwise it does no good from noise considerations. And that's usually done at a point electrically close to the common measurement point, at least if it's a voltmeter or something like that. So basically this is just tied to circuit ground. You just think about it that way. The input, depending on what you're measuring, gets routed around. Let's just take DC volts. So we'd come in here, we go to the common gang of this switch. In DC volts, it's jumpered across here. So the voltage is applied up here. We go through another contact of the same switch here, which brings us up to this point. And the function of this gang of the switch is to jumper around this AC coupling capacitor up here. So whenever you're in a DC measurement mode or off, then this switch makes contact across and shorts out this capacitor. In the 2 AC ranges, this is AC volts and this is AC milliamps, then this switch does nothing, and that makes this capacitor be in series with the input signal. But for the DC volts that we're looking at, we take this path through here, and this capacitor is shorted out and does nothing. So now we continue here, we go through this shielded cable, we come back out here, go through another shielded cable, and we come into the input board. So this looks really crazy here, but really all this is 2 fairly pedestrian op amps, the same model, and they're just connected in series. Both of them are, you know, Fluby dust notwithstanding, these are just normal inverting amplifiers. The input signal is applied to the negative input of this one, the output goes through here and is applied to the negative of the second one, and so on. they both have various things connected to their plus inputs that are used for zeroing, dialing out any offset. So you have some various zero trim pots connected up to the power supply, and you can apply slightly different voltages to the plus input here to have a minimum effect or zero offset. And you also have a test jumper down here. I've highlighted a lot of the jumpers in yellow. You have, for example, plus 7.5, minus 7.5, or ground, which can variously be applied to this blue jumper, and that can be applied to this for various testing and calibration modes. It's diode clamped to ground so that it can't be too far one way or the other from ground. So basically all this stuff here is just different ways for testing or actual use to get the voltage on the plus input exactly where it should be, but normally it's really close to 0 volts or 0 volts. It's just slightly plus or minus from there, not anything further than that. So basically then what you've got is your normal inverting amplifier. It has a feedback path, and the simplest form of it is right here. Just look at this one resistor here. The output comes around, goes through this resistor, comes back to the minus input. That's your basic feedback path, and we can ignore all this other stuff for this moment in the discussion. What else do we have here? Well, there's a high value resistor in series with the input, and then a small value capacitor, and an even smaller value trim capacitor. This is all just to equalize the, not the bandwidth, but the response curve of this amplifier for the different voltages or the different frequencies of input from DC up to whatever that this meter is rated for. So, you know, with DC, it's just going to be going straight through here. As you have, you know, higher frequencies of AC applied, then these capacitors progressively shunt out this resistor here, but that's all just for compensation. You can just think of it as a simple resistor going through here. And then these two FETs are connected up as clamping diodes, so they're just here to protect the op amp in case the voltage here gets too high. And that is actually important, and I'll talk about that a little bit later due to the way this circuit works. But as far as it being an inverting amplifier, you can ignore that they're here. You can just pretend they're not. Then we go through here, and once again we have, in this case, a simpler trim pot for zeroing this op amp, getting rid of any DC offsets. And once again, it has a resistor between the output and the minus input, and all the other feedback paths we can ignore for the moment. And then you're on to this point in the circuit. Well, if you're anything like me, when I first encountered this circuit, I thought, where the heck are the input voltage dividers? You know, every meter I've ever seen has a bunch of resistors on a range selection switch that divides down the input voltage so that you'd always end up with something close to plus or minus 2 volts. It's the usual standard. Almost all the digital meters ultimately divide down the input so that it's within the minus 2 volts to plus 2 volt range. Well, this is an auto-ranging meter. There is no range selection switch. But we have the input, regardless of input voltage, and this can go up to 1,000 volts or so, applied through the switches directly to this point, and that goes right into this op amp. How can that be? Well, just because I hadn't seen it before doesn't mean it doesn't make sense, and it does. So there's these transistors here and here that when they're turned on, they're FETs really, but they're still transistors. When they're turned on, they bring in another resistor and a trim pot to calibrate it that shunts this main feedback resistor, or if we're measuring AC, it brings in a capacitor, but this is the only one we're really concerned about at this point in the discussion. It so happens that with this input resistor value of 10 meg and this normal feedback resistor of 2 megs, that the default amplification of this stage is 0.2. So having said that, let's look at the simpler form of this circuit. This is your basic inverting op-amp circuit. The input, the output, plus input tied to ground or close to it. We've got a 10 meg input resistor and a 2 meg feedback resistor. The gain formula, voltage gain, equals feedback resistor over input resistor, in this case 2 megs over 10 megs, which gives us 0.2. And I've penciled in back here that this resistor here gives us the 0.2 gain. So sometimes we're going to get a signal from the control circuitry that turns this transistor on, and that puts this 500 ohm trim pot and this 20.05K resistor in parallel with the 2 meg feedback resistor here. Let's say this trim pot's set to the middle of its rotation, 250 ohms. These two resistors together equals 20.3K. If we do the normal parallel resistor formula, 20.3K in parallel with 2 megs comes out to 20.27K. It doesn't really affect the 2 meg at all because it's orders of magnitude away from it. But it does have a small effect on it. But essentially it becomes this resistor here. But let's do the math. So it already said it calculates out to 20.27K. If we take that over the 10 meg input resistance, we get a gain of 0.002. So looking at it on my little sketch here, this 20.3K resistor is made up of the trim pot in the middle of its rotation, or middle of its 500 ohm span, plus the 20.05K resistor, makes 20.3K. We do the parallel resistance formula with the 2 meg, we get 20.027K. So here's that formula, 20.027K over 10 megs, and we get 0.002. So by turning on that transistor, we've effectively changed the gain of this op-amp circuit from 0.2 to 0.002. Which is why I've penciled in somewhere here, where did I do it? Right here, that with this guy on, it becomes 0.002 gain. So very low gains. This is basically an attenuator. It doesn't amplify, it attenuates. So in a sense, this becomes a replacement or a surrogate for the resistor dividers we usually have on the input of multimeters to divide the input voltage down. Now the second op-amp is just like the first one. It has this 500K resistor feedback with a 10K resistor input, and that makes this thing have a gain of 50. So this is a gain stage. If we turn on this transistor, the math works out where this op-amp becomes a ×5 gain stage. If I turn on this transistor, it becomes a 0.5 gain stage. So this op-amp here can have any of 3 different gains. This op-amp can have any of 2 different attenuations, all under control of logic that's elsewhere. So I've made up a little chart here. There are essentially 5 ranges this meter can be in auto ranging, but 5 ranges. The lowest range, assuming we're in DC volts, takes the first stage with a gain of 0.2 and the second stage with a gain of 50, and that comes out to a gain of 10. So the overall preamplification stage here has a gain of 10. And the lowest range assumes an input of no more than plus or minus 0.2 volts, full scale. With that gain of 10, that turns it into plus or minus 2 volts. And remember I said before that that is the normal voltage span that almost any digital voltmeter is using for its internal analog to digital converter. That's just a normal range, so that makes perfect sense. If we go up to the next higher range where we're expecting the input swing to be plus or minus 2 volts maximum, we are just going to pass through with no gain or attenuation. Let's look at what happens here. The first stage is still 0.2, but the second stage shifts to a gain of 5, which becomes a gain of 1, which gives us exactly what we want. The signal just passes through both op amps and it ends up coming out with the same voltage. The next range up is expecting a plus or minus 20 volt full range signal, which we need to knock down to plus or minus 2 volts. The first stage is at 0.2 again. The second stage goes down to 0.5, giving us a gain of 0.1, which does that trick very nicely. If we go up to the next range, it's going to be plus or minus 200 volts, knocking it down to 0.2. In this case, the first op amp switches down to its 0.002 gain. The second one is put to its 5, which gives us a 0.01, which gives us the necessary conversion here. And finally, the highest range assumes a plus or minus 2000 volt input, although in reality you're supposed to limit it to no more than 1000 volts. And that needs to get knocked down to 2 volts, so we need an attenuation of 1000. The first op amp is set to 0.002, the second op amp is set to 0.5, and that gives us our 1,000th factor here to attenuate. So that is how this circuit can take very low voltages on the lowest range and boost them collectively to the necessary range into the analog to digital converter, or it can pass them through unmolested, or it can attenuate them collectively to the lower voltages they need to be. And that's the goal of the front end of any multimeter, or certainly any digital voltmeter, is to take the wide span of input voltages and knock them down to something that the next stage in the circuit can use. Well, what's all this other junk up here, you say? In addition to this resistor and this shunt resistor that gets brought in sometimes, or the equivalent resistor and couple shunt resistors that get brought in over here by these two transistors, they also have bypass capacitors. And those are just like what we had over here. They're AC compensation capacitors. You can think of them as being filtering, but essentially they're in the circuit to make tiny tweaks to achieve the best accuracy and stability given different frequencies of AC voltages you might be, or AC anythings that you may be measuring as they pass through these amplifiers. For thinking about them just in their pure DC amplification sense, you can pretend those capacitors aren't there. But we also have this fixed capacitor across the whole feedback network that does the same thing. It's basically filtering. And then there's an adjustable trim capacitor, which again allows you to tweak it a little further. And we don't have that on this stage, but we do have this and we have this. So on certain ranges, this transistor gets turned on, which puts this filter element across the feedback. And again, it's just there to tweak the performance for best results. And likewise, these two can be brought in to put these RC elements across the feedback path to subtly tweak the response of this amplifier in different AC voltage ranges. There's actually, this is a simplified version, it's just showing it as a trim potentiometer. In reality, it's a trim potentiometer, a fixed resistor, and another fixed resistor with a jumper around it that you can cut if necessary to bring this into exactly the right value. But that's all that's happening here. It's just a way of getting the electronics to auto range something that would normally be selected by a big rotary switch on the front of an older multimeter that has lots of resistors to divide down the inputs. After the signal leaves this preamplification, or as they call it here, the PGA, the Programmable Gain Amplifier, we come into the AC to DC converter. This is only used when we're measuring AC volts or AC milliamps. Otherwise it's bypassed. We have two electronic switches on the input, two electronic switches on the output, and they're controlled by the master selection logic elsewhere in the circuit. But essentially one pair of them is turned on at one time and the other one turned off, or the other pair is turned on and the first pair is turned off. So when we're measuring DC volts, DC milliamps, or resistance, it's all DC. So then these two switches here are closed and these two switches here are commanded to be open. Therefore this circuit isn't even in the picture. And we basically just have a bypass, a big short circuit. So the DC signal just comes right over here and goes on out. But if we're selected to read AC volts or AC milliamps, then these two top switches are opened, removing the jumper, and these two bottom switches are closed, bringing this circuit in series with the signal path. Well, we have a little bit of front-end signal conditioning here, and we have an op-amp. Again, it's a fairly pedestrian op-amp. It has negative feedback with a 10 meg resistor. Then it has a feedback path through this capacitor, and that's conditioned in turn by these two diodes. So if the signal is negative here, then you've got a path this way. If the signal is positive, then you have a path this way. And if you think about what this is here, if it's going this way, it's going through this diode, through this resistor, back through these two resistors to ground. So this is really a voltage divider with a small filter capacitor at its junction. So this is essentially a precision rectifier circuit, fairly conventional, and I'm surprised in many ways this is simpler than the equivalent circuits on some of Heathkit's lesser digital multimeters, which use more elaborate versions. This is almost like the simplest textbook version of a precision rectifier. When the input signal here is negative because it's going into the non-inverting amplifier input, the output will be negative. Therefore, you have a path coming around this way. But if the input is the other way around, then you have a positive output, and the path is this way through this diode, through this voltage divider, and then the tap in the middle node of the voltage divider is applied back this way. So you have a modified feedback there. And what that all basically does is it utilizes the op-amp's property of having its output do whatever is necessary, as long as it's configured in a way that it'll work. It'll always try to set its output such that the two inputs are the same. So if we had a plus 1 volt here, it's going to put whatever output voltage is necessary after going through this capacitor, this diode, this voltage divider, and this capacitor. It's going to try to get an equivalent voltage here, and it'll adjust the output until it has a voltage here that matches this. And then we actually tap off of the top of the voltage divider right here, have a little RC network. It's a filter, and then that's the output of the circuit. So essentially what we've done is we've taken the input circuit, we've rectified it by this diode, and because the diode's in the feedback path, the amplifier adjusts to compensate for the voltage drop in the diode, and therefore we have no signal loss. The signal just passes through, rectified but not attenuated by the diode's voltage drop. And then just to give the op-amp something to do when this diode here is reverse biased, the other side of the waveform, then we just run it through this other path here, but we're not actually using that. We're not taking a measurement there. It's just giving the op-amp something to do on the other side of the AC waveform. And I should point out that this capacitor here is important because you don't want this circuit working on DC voltages. You only want it to work on AC voltages. So if some DC voltage component is riding piggyback on the AC waveform, it'll be rejected or blocked by this capacitor, and only the AC part gets through, is converted to DC, and picked off here, filtered a little bit more, make sure it's really a DC signal, and then brought through this electronic switch, and then it goes on out. So we always end up with a DC voltage here. All digital multimeters, well, and certainly all digital voltmeters, and by extension digital multimeters, have to at some point convert the analog signal to a digital signal. And this is where it's happening here. It's doing it in the normal way. It's using an input buffer. Doesn't change the signal at all. It just makes sure that anything that's happening out here with impedance changes and things do not affect whatever's happening down here, or this loading down that. So it just passes through without being molested. There's an integrator here, which is just an op-amp with a capacitor in its negative feedback loop. And it's got some modifiers up here, but basically it's just the capacitor coming around here. We have an auto-zeroing buffer circuit that provides an extra feed into the same point here. So we have the signal from the input buffer, and it's summed with the output of the auto-zero buffer. And that's just a more advanced feature of this, that it takes into account any offset that might creep into this circuit and skew your results. When you apply a DC voltage to the input of an integrator, the integrator charges or discharges the capacitor in the feedback loop, and because it's in the feedback loop, instead of getting a characteristic capacitor charge curve, you get a linear ramp. It ramps at a linear rate, so the signal is ramping up or it's ramping down. And then that is compared to a reference voltage with a comparator, and that detects when the ramp has increased or decreased to the reference voltage, and by timing how long it takes the ramp, to get to the reference voltage, you can determine how big the input signal was. And that's the essence of all of these circuits. Now this is pretty early here. This is early 70s circuit design. They did not yet have the big monolithic single chip analog to digital converters for digital voltmeters. And this is a siliconics solution, a fairly early one. And it's in a 2-chip set. It has this one, it's the LD111, and that's one chip in a chip that in a pair that includes the LD110. So it's known as the LD110, LD111 chipset. They always go together. I'll talk about this one a little later. It has only 3 control signals, really. This is an input to the circuit block here that determines whether we're measuring the input signal or whether we're zeroing the circuit. So that changes this switch here. It's an internal electronic switch, and there's another one here, and it just connects these components in different ways so that we can be calculating any zero offset there is and compensating for it by the way this works, or if we're actually doing integrations as part of measuring the input signal. So that's all under control of the other IC in the pair. The signal comes in. Then you have your comparator output that tells the control chip whether the ramp has reached the reference voltage. Therefore, we know from how long it takes to do that what the input signal is, so that's an important output from this chip. And then there's a reference control input that comes from the other chip and switches this circuit here, and then that messes with the other circuits, and I won't go into all the weeds on that, it's just going to take too long, but that's basically what it's doing. And this is using a version of dual slope, which is better. Most of the other Heathkit digital multimeters up to this point in their product line used a single slope integrator, often done with discrete components. But with a single slope, you would have to recalibrate it a lot because any number of small changes in other components, temperature or what have you, you don't know if the rate of integration is a little higher or a little lower than it should be to get the right amount of integration time proportional to your input. So by a dual slope, it ramps one direction and against a known value, and then from that it figures out how it has to interpret the amount of time it takes to ramp back up. That's a simplification, but that's basically what's happening. So it's a dual slope, and it also uses a reference that's sort of in the middle, so it's actually ramping from below a reference voltage to above a reference voltage and ramping back down. And based on that, it can tell whether the input voltage is positive or negative. So that's another refinement. So that gives you your plus or minus indication on the display ultimately. So that's all I'm going to say about that circuit, but this is half of the guts of a typical voltmeter analog to digital converter. And by the way, that chip is on the input circuit board. Since that's a largely analog circuit board, it belongs on there. And it communicates over those 3 signals I mentioned before to its sister chip or its partner chip, the LD110. This has all the logic operations instead of all the analog operations. It's actually fabricated with a very different process suitable for digital operation, whereas this chip is fabricated in a very analog process, which is probably why they did them in 2 separate chips. It just made chip fab easier in those early days. What we have inside of here is a block of control logic, which is too complicated to get in here, but it has that measurement or zero control signal going out. It has the reference control signal going out, and it has the comparator signal coming in. And that's, like I said, it's its sole communication with the other chip. There's a 555 timer down here, rigged up in a very conventional astable multi-vibrator circuit. It produces an AC, or not an AC, but a frequency output. I want to say it's something like 22 point something kilohertz, which is brought into the clock input of this IC, and there it gets divided down. It's a time-based counter and two-phase clock, so it gets used in several different ways within here, but everything is synchronized to a timed cycle in this chip. It has a 3.5 decade counter. Remember, I said that when we're integrating here, it integrates faster or slower depending on the magnitude of the input signal. So if you have a low voltage input, the ramp is slow to gain voltage, or lose it if it's going in the other direction. If it's a higher input voltage, closer to that plus or minus 2 volts, then the ramp gains or loses voltage quicker, so it's a steeper ramp. And within the specified amount of time that it has, it's going to take more or less time to reach that reference threshold, and that starts and stops a counter. So that's the counter down here. It's taking this divided down signal from the 555 clock and counting it until such a time that the comparator says that the ramp has crossed the reference voltage, so stop counting. And whatever count you have left in the counter is the numerical equivalent that's proportional to the input signal. So a smaller signal, it'll be a lower count, a bigger signal will be a higher count. That value is then latched, because then this gets reset, but you still want to hold the value in the latches. Then it goes into a multiplexer that figures out how to drive the display. And the time base here also has a 1 of 4 decoder, because there are 4 digits in the display, and the multiplexer only drives 1 digit at a time. Remember, the entire 3.5 digit, or here it says 3.5 decades, same thing, value is latched in here, all 4 digits of it, and it's called 3.5 because the least significant 3 digits can be any value, whereas the most significant digit can only be 0 or 1. That's because it goes up to 1999 total count. So that value is held in the latches. The time base counts up 1 to 4 over and over and over again, and that 1 to 4 references which digit we're thinking about at any given moment. That information's fed into the count multiplexer. When this decoder here says we're thinking about digit 1, the least significant digit, it tells the multiplexer to kick out the value from the latch that applies to the least significant digit. That's buffered. It's sent out as BCD data over 4 wires, and that goes over here and goes to the display board. Then when the clock kicks up to 2 on the decoder, that tells the count multiplexer to output the BCD code for the second digit, and so on until it's done all the digits. Now, for some perverse reason on here, I think the order of multiplexing is something like digit 1, then digit 3, then digit 2, then digit 4, but that's transparent to the user, certainly. It doesn't matter which order you do it in. It's just the way this one does it. So we have that which digit we're talking about, digit 1, 2, 3, 4, and the BCD values, A, B, C, and D, for what the value of each digit is. And that is the output of this IC. Going up to the display board, the display circuit board if you will, we have down here the digits 1, 2, 3, 4 signals coming from the IC we just discussed, and those go to these 4 Darlington transistors, each one of which is connected to one of the 4 digits. There's a separate integrated display chip, if you will, for each of the digits. Each one has its own common cathode, meaning that the conventional current is going this direction through the LEDs and out the common cathode through the transistor to circuit ground. But only one of these is turned on at a time. That's because of the multiplexing I discussed already. Meanwhile, the signals, the BCD values from the master chip are brought into this. This is a segment decoder. It takes the BCD coded value for each digit and it converts it into the segments A, B, C, D, E, F, and G, which follows the convention of the 7 segments on the display, A, B, C, D, E, F, and G. And then those signals come out here. Each one goes to a transistor, which is in turn connected to the plus 5 volt display power supply we talked about already. That's that higher current power supply that's only for use by the display. So that voltage is brought down here. It goes through whichever combination of these 7 transistors are turned on by this chip, and that applies those voltages to the 7 inputs on each of the digits except for the most significant one. And it actually looks like there's 5 digits here, and in a sense there's actually a 5th chip, but it's a special chip. It's not the same models as these 4. This one here is only used to display 1, even though it's shown here as displaying 0. And it actually, well, I should clarify that. This one can display 0 or it can display 1. It'll do one or the other at various times. And then this one is just used to turn on the plus and minus signs. It has the capability of displaying a 1, but it's not being used for that purpose. So all these are connected together in sort of a bus arrangement, and then whichever one of these is turned on by these lights up and displays the desired pattern. Then it switches to the next digit. The code's coming up here, change, turn on the proper segments for that digit, and so on. Now there's a couple extra goodies up here, because this display is only being tasked with displaying a 0 or a 1. There's a little bit of diode logic up here to determine what it should be displaying. It's not driven by the A through G lines that the other ones are. Well, 2 of them are. For displaying a 1 it is, but for when it's time to display a 0, this chip over here doesn't know how to display a 0, so this logic up here figures out when it should be displaying a 0, and it turns on this diode logic which energizes the segments sort of manually to turn on and form the shape of a 0. So that's what that's doing. Now the decimal points are handled a little differently. This decimal point, this one, and this one are used. This one is not. So those points are all brought out. Let's see. Yeah. So this is the decimal point for this guy. It goes over here, here, and here. We're not doing it on this one because, like I said, it's not used. You have to imagine those connecting over to here. Each of those has its own transistor. Those are just like these transistors here, except they're not driven by this BCD to 7 segment decoder chip. They are instead driven by these mysterious signals that go off and they jump down here and they go through these diodes and they come down here and go to this big cluster of logic down here. So it's time to talk about ranges. This block of logic down here, hiding below the digital A to D converter chip, it's all discrete logic, and it's charged with doing the auto ranging functionality. And it uses a fairly simple scheme. It starts with, I believe it's the lowest range, and it's getting that because there's a power on reset or power on clear here with a resistor, a capacitor, and a diode. It essentially just has a counter here. This is a little counter. It's capable of counting 0 to 10 or 0 to 9. And it has an input that makes it count up. You pulse this and it counts up 1, or you pulse this one and it counts down 1. And you know, it can't go higher or lower, but it counts within its range. And then the output is expressed in terms of a BCD value, A, B, C, and D. It's binary coded decimal. And then that's fed into this chip, which is a BCD to decimal decoder. And it has 10 outputs, 0 through 9. So as this guy counts up from 0 to 9, one of these 10 outputs will turn on. This chip is capable of being preset, but we're not using that feature here. So all the preset terminals are just tied to ground. That feature is disabled. And the load input that would be tied into these is disabled by tying it high. So this is a very simple device. It can be cleared to its lowest setting, which is 0. It can count up from there. It can count down from there. And basically, it uses a little bit of logic here. It's looking back at both the which display digit is turned on, and it's looking at which BCD pattern for the currently displayed digit is on. It takes all those values, and in this logic right here, it can figure out if the displayed value is bigger than 1999, which is an overrange, or it can detect if it's less than 180, which is considered a good value towards the bottom of the range. Remember that this can display from 0 to 1999 on the display. So it's sort of manually looking at the actual signals going to drive the displays, and from that it figures, is it getting a value higher than 1999, which this chip can generate, and if so, the range we're in is too low. It's overrange, so we need to shift to a higher range. And if the currently displayed value is less than 180, then maybe we should be in a lower range than the one we're currently in. So that's all this logic does. It always starts out at the lowest value, and then it looks to see what the chip here is trying to display. And let's say that it's in a range that's too low, so it's overranged. This logic detects it, and it comes over here and generates, through this gate here, it generates an up count signal, a pulse that causes this to shift up from 0 to 1. So now it's in the next highest range. That's decoded here, and it, instead of the 0 output being turned on, the 1 is turned on. Well, in this case, they're both tied together, so it treats them as the same count. But what if it shifts up again? Then number 2 turns on, and these guys are off. So by that way, it's able to constantly, every time a measurement cycle is taken, if it still is overranged, it just keeps toggling the up count until we get to a range where the output is not overranged, and then it stays there. On the other hand, if your value that you're measuring starts dropping and you get below a displayed value of 180, it says maybe we could do a better job by shifting into a lower range. In that case, this gate down here generates a pulse which causes it to count down one to the next lowest range. We're only using 5 ranges here, and that involves outputs 1, 2, 3, 4, and 5. All the other outputs, 6, 7, 8, and 9, well, 6 and 7 are just tied to 5, so the rest of the circuit treats those as being the same. It's the highest range. And then if you really go higher, then it's considered an illegal range, and it's detected by this circuit here that just says something's screwed up, let's reset the range counter and try again. So it generates a pulse to the clear input, which takes this back to the lowest range, and it starts at the bottom and works it out again, so that it handles situations where everything goes kerflooey. And the power on signal when you first turn on the meter also generates the clear, so we always start at the lowest range. So that's what's going on there. You can block these 2 gates. These are logic gates, and they only produce signals to the counter when this input or this input is turned on. And normally they're pulled up by this resistor to a logic high, which enables these gates to pass signals through them. But that goes to the front panel auto and hold switch, and if you put the switch in hold, that grounds the signal, pulls it down against the pull-up resistor that disables these gates. The up and down signals can't get through them, and even though the rest of the circuit's trying to shift up or down through the ranges, it's not allowed to, and it just stays in the range that the user is telling it to stay in. All of these outputs are open collector, which means when they're logic high, they're not connected internally. It's just like a disconnected pin. And when they're low, they're connected to circuit ground. So they all need to be pulled up to logic high by these pull-up resistors. And you'll notice here that these chips are working on a 5-volt logic supply. Over here, these logic signals are working on a 12-volt supply. That happens throughout this circuit. Some of the logic is running on plus 5 volts, and some is running on plus 12 volts. It just depends where you are in the circuit. And there's a fair amount of level shifting that's going on, and here a number of the components are selected because they can work at either voltage, but we can just ignore that for the moment. Now, those 5 signals for the ranges we're in are conditioned here. Here's range 1, and then it's inverted, and it's the inverted range 1. So we have a, well, it comes out naturally as inverted because when, for example, this output says we're in range 1, it's pulling it to ground, which means it's at a logic 0. So when we invert it, this signal here is logic high when we're in range 1, and its natural uninverted state is 1 with a bar over it, meaning it's the inverted version of it. Same thing for range 2. Range 3, we only need it in the inverted logic true form. 4 is available both ways, 5 is available both ways. And that produces this huge bus of signals. And those wrap around, and they go all the way around here, and they come around here, and they go to all of this combination logic here. And I don't want to get into all that, but this is how it's figuring out things like which decimal point should be turned on. It can figure out, for example, we're in the lowest range. Well, that says we should have the lowest decimal point. And we go over here, and it goes up to the decimal point circuits here and turns on the appropriate decimal point. This block over here is looking at the 2 range or the 5 range, and whether we're, doing some other things. It's all combinational logic. I don't want to go to every permutation here, but it's figuring out all the different conditions the meter can be in and based on that, which of the decimal points should be turned on, and that's why these blocks of logic are here. There's also this extra block over here on the right, which is not associated with decimal points, but it's doing the same kind of logical job up here, but instead it's turning on these two transistors, a regular transistor and a Darlington transistor. And basically what that's doing is it's wrapping back around here, and it's turning on these two discrete LEDs, which are not part of these LEDs. They're down below them. And one of these is the LED that says when we're in a resistance measuring mode, it tells us that we're measuring kiloohms or displaying kiloohms. The other one turns on to say we're displaying megaohms. So that's all figured out by this piece of logic over here. And then these are the LED drivers. So those same range signals are brought up here. There's a bunch of test points so you can monitor them easily. And they're used by several things. It's used by the ohm meter logic block here, or circuit block. It's used by the current measuring block, and it's used by the programmable gain amplifier circuit block. So all those are brought up to here. We have more combinational logic up here. For example, if these conditions here are true, then you turn on this transistor, and that passes through here, and it goes up here, and it turns on this transistor here to shift the attenuation of this first op amp, as we discussed before. So that's coming from this guy. And an inverted version of that is brought up here, and it's used to control this transistor on the second op amp when we need to bring in this circuit here, as I already described in the AC range. So we see the same kind of thing over and over, where there's a combinational logic block driving one or two transistors. In this case, two combination logic blocks driving one transistor. The same kind of thing here, and a more glorified version of it here. It's all just figuring out with the various permutations of what's going on with ranges and so on, which of these transistors should be turned on to shift the programmable gain amplifier to those different gains we talked about before. So that's all that's going on there. It also gets used to determine whether we're in AC or DC mode, but that's not coming from the range logic. That's coming from other signals. There's a single signal here, which is the AC. When this is on, we're measuring AC, and it goes over here, and it comes to this block, and from that it's able to turn on or off these four electronic switches appropriately for how we're going to condition AC signals or not. Now, I promised earlier to come back and talk about what these guys are doing, and I said they're clamping diodes essentially on the input of this first op amp. Remember that we can be exposing this point here, not here, but this point here, to at least 1,000 volts in the highest voltage range. So a really high potential compared to ground just over here. Now you have this huge resistor here, followed by clamping, which is just fractions of a volt here that it's clamping to. They're connected to the plus 7.5 and minus 7.5. The actual voltage can be 1,000 volts over here, but on this side it's not, because you may remember basic op amp theory. when you've got a inverting amplifier like this negative feedback, this point is always going to try to be the same as this point, and this point is basically 0 volts. So the op-amp is always working to maintain this point at a virtual ground level, and if it gets much away from that, one or the other of these transistors will turn on and clamp it to just a few volts above or below 0. But if everything's working properly, this should never get that high. If you have say a 1,000 volt input here, you're going through this really big resistor, and that results in a very small current going into here, but no current flows in or out of an op-amp in this configuration. And that's because that current is actually sourced through the feedback path from here. So let's say we put in a voltage that resulted in, I don't know, 1 milliamp. I'm just pulling that out of the air. It's probably nowhere near that high. Let's just say 1 milliamp to keep it simple. That's going in this direction. It can't go into here because no current flows in or out of op-amp inputs. That means the 1 milliamp must be going through our feedback resistor and going to here. Well, that means this has to be negative. Well, it is, because we're trying to apply a positive potential here, and that would, on an inverting input, drive the output negative, and therefore there is a place for this current to go. It can go from a positive here over here to the negative potential at the output of the op-amp. So this point never sees, if everything's working properly, anything but 0 volts. This op-amp is not going to blow up because you've got 1,000 volts sitting out over here. That's something I scratched my head about for a moment. How can they do that? And say, well, of course. Yeah, it's 1,000 volts over here, but then there's a 10 meg resistor going to a place that's a virtual ground. It's basically 0 volts. And there's no problem having 1,000 volts across that 10 meg resistor. But that's a very critical component there, right? If you replace this with something else, then bad things are going to happen. The other thing I didn't mention before is that these are inverting amplifiers. I said that, but the fact that there's one following another one, when you have a positive input signal here, it'll be positive over here, although it'll be negative in between them. And if you have a negative here, it'll be inverted to positive, then re-inverted to negative. So the polarity is always the same from here to the output of the precision or programmable gain amplifier. Something else I want to mention before I forget about it. Up here we have our plus 12 volt, and there's a trimmer, I sub Z, that feeds in. There's a fixed resistor and a Zener diode. It's producing 6.2 volts up here, and it's filtered, and that's used as the reference voltage by this circuit we already talked about, the integrator circuit. It's also used up here for this op-amp circuit. Depending on the position of these jumpers, you can move this jumper from one position to the other position. And there's a voltage divider here. So we're dividing down that 6.2 volts here into 1.9 volts and 0.19 volts. And depending how you move this jumper during calibration, you're tapping off one of those two voltages into this op-amp. This is something that confused the heck out of me when I first got this meter, because I hadn't purchased the documentation from it yet. I didn't have a schematic or anything, and I saw an empty IC socket on the input circuit board. And I thought, oh my god, it's missing some part, and it's probably something that blew up, and it's probably some weird IC that I won't be able to find, even if I know what kind of IC is supposed to go there. I thought it could be a deal breaker right away. And I envisioned, you know, tons of hours trying to reverse engineer the circuit and figure out what was going to go here, and then not being able to buy the part. Well, thank goodness for buying this manual from Manual Man. I think it's manualman.com. Kudos. He can provide a lot of manuals, either originals or good reproductions of them. He's the only place I found that had the manual for this meter. Literally the only place. There's actually two manuals. There's the assembly manual and then the operation, calibration, you name it, manual, theory of operation manual. That's a separate book, and that's what he had in reproduction, whereas I was able to find the assembly manual several places. That doesn't tell you anything about how the thing works. So this op amp is only needed during calibration, and it's the same exact kind of op amp that's used here in the AC to DC converter or precision rectifier circuit. And this part is not used during the time when you need this signal. That signal is brought around here and through another jumper that's either tied to ground, that's the normal position, or it's tied in to this input here. It's a way to force an input to this first amplifier in the programmable gain amplifier circuit during certain parts of the test. You'd like to have a well-known precision voltage reference applied here instead of a normal input signal. And so when you do that, you power off the meter, you pull this IC out of its socket, you go over and plug it into this empty socket, you move this jumper to whichever position is necessary, and this is wired up as a buffer. It has no gain or attenuation, and it's a positive input, so it doesn't even invert it. It just takes whatever's here and copies it to the output. This is higher impedance, this is very low impedance. So we run over here through a shielded cable, we come to this other jumper, and again, normally it's just tied to ground, it's just something to do with that wire. But we're in that particular test mode, we move the jumper to the calibration mode, and now we're taking that 1.9 volt reference or the 0.19 volt reference and applying it to the input of this circuit. And guess which ones are, which voltages are used. One of them is going to be used when we're in the ×2 gain mode of this amplifier. The other one's going to be used when we're in the 0.002. Anyway, so that's what that's all for. And then when you're done with calibrating this stuff, then you power off the meter, you unplug the IC and move it back to here for actual operation. Are we bored yet, or are insomniacs rejoicing? Might as well forge ahead. I've spent enough time on it already. It's a good thing I'm not going far into the weeds on this. So let's say we want to measure current with this. Let's see what happens. I'll just draw a line here for DC milliamps. This is where the switch is going to be. Here, 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 and here when we're in the DC milliamps mode. So we already know that the COM terminal is always tied to circuit ground, so we don't even have to follow that one. The input signal now comes here, and it goes to this gang, and it comes down here, goes through here, goes through the shielded cable, comes out here, goes through the dedicated fuse that's only used for milliamp measurements. It goes to a voltage clamping circuit made out of basically a diode bridge, and then it's applied to this bunch of shunt resistors, which goes, guess what, back to circuit common and ground. So the current has come in, it's gone through the switch, it comes down here, it goes through one or more resistors back to ground, and from there back out the COM terminal. So we have a nice loop for your current path. It's really that simple. Now, depending on what range we're in, one of these switches will be closed. Let's just say we come in here and this switch is closed. These other guys are open. So we're bringing the current in here, and it goes all the way through all these resistors and back out through the common terminal. So that's obviously used for when we have a lower current and we need to run it through all these resistors to develop enough voltage drop to be worth measuring. If we have a somewhat higher current, then maybe this switch will be closed instead and the current goes through fewer of the resistors. And finally, at the highest current range, the bottom switch is closed and the current only goes through a 0.1 ohm resistor. But because it's a high current, it still develops a reasonable voltage across that tiny resistance. So that's very conventional, but usually this is done with a selector switch, and here it's done by 5 relays. Now the 2 relays here, you can see they're controlled by these circuits. These are the coils of the relays, and they're controlled by transistors, and actually these other ones are just the same. They all have transistor drivers, they all have a freewheeling diode across the coils, and that's there so when you de-energize these coils, there's the magnetic field that's built up in the coil, and it's going to collapse, which is going to generate a high reverse voltage across the coil. And when that happens, because it's reversed, then this diode acts as a shunt and it shorts out the coil, thereby immediately dispensing of that energy. It just dumps it into heat essentially, but it's a tiny amount. It's not a lot of power there, but there's a high voltage potential. If you didn't have this, then that high voltage would snuff this transistor. It would severely reverse bias it and probably blow it up. So this diode here keeps that from happening, and it prevents problems in the rest of the circuit. So there's the same thing over and over. This is a driver circuit. It's an integrated circuit, and it's controlled in turn by these resistor capacitor diode networks that, guess what, come from those 5 ranges we were talking about. 1, 2, 3, 4, 5. One of those ranges will always be on. When it first turns on, it goes through this diode. It doesn't actually have a value there, but I think these are all 10 meg. It's kind of interesting that they did, it's just on the fold. It does say 10 meg there. So it's got a 10 meg resistor, and then that charges up this capacitor until it reaches a high enough voltage to cross the threshold of this IC, at which point the output turns on. It turns on the transistor, turns on the relay coil, it closes a contact. You obviously have a different charge-discharge path here. And then when you're going the other direction, this is reverse biased, so the capacitor discharges through this other value of resistor. So it's just fine-tuning the turn-on, turn-off times of these relays. And I think, although I don't know if I've seen an explanation of it, I'm just guessing, that this is there to provide a sort of a make before break. When we're changing ranges here, it's a good thing to have the old range's contact stay closed very briefly while the new range's contact closes, so we don't have an open circuit here anywhere. It always maintains a circuit. So let's say it's switching from this range to this range. This guy's already closed. We're switching to this range. This guy closes, and while it's taking time to close, very small amount of time, but it's taking some time, this guy remains closed during that interval, and then after this has had time to close, then this one is allowed to open. That time delay is not generated by logic. The logic just shifts gears from one range to the other practically instantaneously. So this little circuit on here allows me to hold on a relay that's currently turned on it turns it on very quickly, but it turns it off slowly. And that provides that make before break functionality here. And because the higher currents are taking these paths down here, these contacts need to be capable of handling a lot more current. And therefore, these two relays here are much bigger relays. And for the lower current ranges, they're much smaller relays. They're basically reed relays. On my part of the video where I talk about the circuit board, the main circuit board, I pointed out that there were 2 large relays and 3 reed relays sitting all side by side, and that's these guys. So regardless of which path we take, we're developing a voltage across whichever resistors in this series are connected to have current going through them. Let's just pick this one. Let's say this guy's closed. The current's going this way. So I'm developing a voltage across these resistors here. But these resistors are still connected, and they're not going anywhere here because these relays are open. So we're basically using this as a measurement path. Whatever voltage is developed down here is just measured through these resistors, and it comes back, it goes through here, and we get up to this switch on the function switch. We go through that contact I penciled in, and it goes up here and is presented to this gang. And if we were measuring AC milliamps, we would be routed through this capacitor, but we're in DC milliamps, and that's one that's closed, so the capacitor is shorted out, and we come down here, we go through here, come back and go through this one, and we're up to the programmable gain amplifier. And the circuit would be just the same if we were measuring AC milliamps. The signal path is just exactly the same. But another gang of the switch elsewhere is telling the meter whether we're measuring AC or DC. So, by the simple expedient of measuring currents by passing them through some known shunt resistors and then measuring the voltage drop across those, the voltage drop is always proportional to the current, and then just measuring that voltage drop in the same way we measure AC or DC volts. That takes care of the current ranges. So now I've discussed how AC and DC voltages are measured and how AC and DC milliamps are measured. So that leaves resistance. And it's really the same thing. We pass a current through a resistor and measure the voltage drop across it. But in the case of measuring milliamps, it's the resistor we know and the current we don't know. In the case of measuring resistance, it's the current we know and the resistor we don't know. The resistor we don't know is the one under test. So let's go back here and look at how it's connected. I've redrawn my pencil lines. They're here, 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 and here. As before, the one side of the resistor that's being connected out here, the resistor under test, is just between these two terminals. So one side is connected to circuit ground. The other side comes in here. It's brought through this switch. It comes down to here. The two resistance ranges, the low voltage range and the higher voltage range, are treated identically by these switches. So we come through here, we go down here, through this wire, and we're presented with this point in the circuit. This is where the current comes from, so I'll discuss that now. Once again, we have our 5 ranges up here, and those are brought to this IC. It's just a hex buffer chip, so it inverts the signal. If the range is on, then the signal on the outputs will be off, which is appropriate because we're going into PNP transistors here. This is plus 12 volts up here. There's this Zener diode voltage divider with a 3 volt Zener. a 6.2 volt Zener, and then that continues back here and goes through this 300 ohm resistor to a point that's ground, because this signal here, this is a hex inverter, so there's 6 inverters in the IC. We're using 5 for the ranges. The 6th one we're using to just determine if we're measuring resistance or not. So a control signal from somewhere else comes down here and it says, hey, we're measuring resistance. It's high, which in this case is 12 volts. It's running on a 12 volt logic signal. So that's high when the meter's in the ohms mode. That inverts to a low, which provides a ground here essentially. So current can flow through the plus 12 volts through this Zener, through this resistor, and to ground. So we know we've got 3 volts less than 12 volts. That's a regulated 12 volts, so we'll have 9 volts here. And then we'll have, well, 9 volts here, it's the same point. Then down here we'll have 2.3 volts, or thereabouts. It's 6.2 volts lower than the, 6.2 volts lower than the 9 volts. So, this measurement here is a little confusing, but we know we have 6.2 volts across this. And then the remainder of the voltage of the 12 volts is dropped across this resistor. Then this is the one we're interested in here. We have a resistor voltage divider across this 6.2 Zener, which gives us 8.6 volts at this point. That is applied to the plus input of this op amp, another fairly plain vanilla op amp, and it's connected with a capacitor in its feedback loop, but that's really for stabilization. It's not the primary feedback. And then we have the input signal to this is coming through one of these 5 circuits, only one of which is turned on depending on which of the 5 ranges we're in. So let's say we're in this first range. This range will be turned on here. This will go to low. That pulls the base of the PNP transistor to ground. Because it's a PNP, that turns it on. If it was an NPN, we'd expect to have a voltage applied here instead of a ground applied here to turn it on, but it's a PNP, so that turns it on. It takes this regulated, Zener regulated 9 volts and sources it to here, and you get some thing going through this trim pot and this resistor, then through this resistor to the input of this op amp. Well, let's say no current is flowing out here yet, so pretend this isn't here. The only place for this current to go would be through this transistor, through these 2 resistors, through these guys to here, but no current can flow into an op amp input, so there actually is no current. If there's no current, then these resistors are essentially infinite, or negligible, depending how you look at it, and you're essentially applying 9 volts to this input, or you're trying to, but the op amp's going to work to make sure you don't. And this input is 8.6 volts, so you have a higher voltage applied to a negative input than you do to a positive input. The op amp is going to react to that by saying, well, the input, it's like a comparator at this point instead of an op amp. And it's going to say, well, I've got a small difference in the plus and minus inputs. The minus side is one of the higher voltage, so it drives the output hard in the negative direction. Well, here we have an FET of the type that is turned on when you have a negative voltage here. A negative voltage applied to this forward biases this junction down here, and that turns this FET on. the way it's wired to this bipolar transistor is that turns this guy on, which now provides a path from here on out through this diode and back through all that stuff I showed earlier that goes to the resistor under test, and then from there to ground. So all of a sudden we now have 9 volts going through here, and it has a way to go on out through the resistor and back to ground. When that happens, now you don't have the same voltage here, because now there's a current. Let's say it's 1 milliamp. Now you have a voltage drop across these where you didn't before. So now this voltage isn't as high as it used to be. It used to be 9 volts because there was no voltage drop. You don't have a voltage drop if there's no current. Once you start having current, you get a voltage drop. That means this point can no longer be 9 volts. It's a little bit less. And if it's a little bit less enough to be on the other side of the 8.6 volt reference, that means that now the plus input is higher than the minus input, and it's going to try to push the op amp in the other direction, which reverse biases this guy, turns it off, which turns this guy off, which means there's no current going this way anymore. This essentially forms a feedback loop, and it's a negative feedback loop, just not the conventional kind. If the current gets a little too high, the op amp changes what it's doing, turns these transistors off some, reducing the current. If the current gets too low, then the op amp does the opposite thing and results in turning these on a little bit more, increasing the current, and thereby the current is regulated, and the amount it's regulated is based on what this resistance is, which is calibratable by the trim pot. If you turn on this transistor instead for another range, you have a different set of resistances, but it's the same operation, you just get different amounts of current, and so on for the 3 other ranges. These diodes are in here just to handle the contingencies, basically. I won't get into them, but they're just there to make sure that these voltages don't swing in ways that could damage this. What if you connected a capacitor out here or something instead of a resistor, and now you've got a voltage there that's brought back here, and what if that, reverse biases this guy and damages it, for example? Well, then this diode would kick into action and prevent that from happening. It's that kind of thing. It's just to protect these transistors against contingency situations. But that is the essence of how we get a regulated precision current, a different current for each range. It gets passed through the resistor out here, and that forms a voltage drop across the resistor under test. So now, let's go back and look at that same signal. We have to follow this back. That was back to this point, right? Somewhere along there we have to get this guy. Okay, yeah. So this was the path that we were using to get current into the resistor under test, and a voltage developed across that resistor between this point and ground, and that resistor, or that voltage, comes up here, goes to the second gang of the switch, goes through this contact I penciled in here, and now it goes down this way, goes down this wire. Hopefully I don't lose track of it. And it goes into this op amp. Well, this op amp is another one that's set up to be a unity gain buffer, non-inverting. So once again, it's just making a copy of the input signal, but it's changing it from a high impedance to a very low impedance. It's just a buffer. So the buffered voltage is exactly the same, but now it's something we can use without fear of skewing the voltage under test, which is coming from the resistor under test. So the buffered signal comes back here, and it comes up to this switch, and it goes through this contact and comes up here, and once again it's applied to the gang of the switch that deals with AC and DC. We come down here. This is the contact. It's shorting out the capacitor, so the capacitor is not there. And it comes back around here, and it goes up to the programmable gain amplifier that we discussed before, and it's treated just the same from that point on out. There are some nuances I didn't get into here, trying to keep this as brief as reasonable while being reasonably thorough. Yeah, I think oh yeah, here's another gang of the switch. I did not talk about that other than to say there was one. This is another gang of this switch we were looking at over here. And there's another gang that we already talked about, and that's the one that's used as the power switch. But this is the remaining gang here. And it has a pull-up resistor from plus 12 volts. It goes into the gang of the switch. And then depending on which mode we're in, we come over here and we have some good old-fashioned diode logic. So let's say we're in DC volts. That's passed through here. I'm losing my pen here. It's passing through here, goes down here, and that's the so-called, I can't hardly even read it, V something or another, voltage, current, low, Z's or something. I can't read it. It's too darn small. And that comes over here, and it's got a resistor to ground, and it's over here, and it's being used by this gate, which is being used by this gate, and that influences the decimal point, but not directly. It depends on other stuff, which is in turn tied back to the range logic. So again, it's all this combinational logic down here is figuring out, based upon what function we're in and what range we're in, where certain other things should be happening. And some of that deals with the decimal point, some of it deal with other things. But part of it gets fed back to all these other circuits I already talked about that change ranges up here, change ranges down here, affect how the decimal points work, decide if we should be shorting out the AC to DC converter or not. That's all affected by this diode logic up here. Depending on which function or mode we're in, it influences these various signals that get used in all these different ways. And we'll be here for another 3 hours if I try to follow all those through. But that's how the meter knows whether we're measuring AC volts, DC volts, AC milliamps, DC milliamps, checking the battery voltage, or if we're in the high or the low voltage ohms modes. And let's see, did I forget anything else? I think I mentioned that the plus and minus on the display is controlled by these transistors, which in turn are controlled by this logic here, which in turn is influenced by the mode that we're in, and a sine signal, which in turn comes out of the analog to digital converter IC. I mentioned before that because of the way the slope is biased above a reference voltage, it can tell whether we're integrating from a negative input voltage or a positive input voltage, and therefore this logic knows whether we're counting a positive or a negative signal, and if necessary, its control logic says, hey, we need to have a sine, and then that's brought up here. It's combined in logic with the mode that we're in, and that determines which of these transistors should be turned on, and that determines whether we should have the plus or the minus segment given a path from the 5 volt plus 5 volt display power supply. It'll either go through here and turn on the plus, or it'll come down here and turn on the minus. And this is just an inverter here. So that's how that's worked out. I don't think I'm forgetting anything else. I'm sure there's some other little subtleties. Oh yeah, there's a strobe function in here, and I mentioned before that the analog to digital converter IC pair is constantly running in a repeating high-speed cycle between auto-zeroing itself and actually taking measurements. And that's a signal which is kind of like a clock signal, and it's synchronized to the operation of the meter. And it's used in a couple of places for other reasons, just because it's a high-frequency signal that can come in handy. But it's brought up here through this gate, and that in turn goes, where does it go? Down here and back up here, and it goes to the lamp test pin of the segment decoder. Remember, the one that converts the BCD data for each digit to the individual segment signals for whichever digit is being currently displayed. But there's a lamp test terminal on it, and if you energize the lamp test terminal, it disregards the BCD data and it just turns all of the outputs on to basically test that all the segments are working. So what happens if you modulate that lamp test signal on and off at a high rate of speed, which just happens to be coming from this measurement/0 signal through this logic, essentially what it does is it goes from displaying normally to displaying all digits turned on, then back to displaying normally and alternating at a high rate of speed. And that appears to the eye as if the display is flashing. You can still read it, but it's got a kind of a stroboscopic effect to it. And so that's what's going on there. If you get into a range where the auto range circuit can't make sense of what's going on, the other logic I've just described says, hey, we need to flash the display to tell the operator he can't trust the value that's being displayed because there's something going on that's not being handled by the normal automatic functioning of the circuitry. It's been detected that something is ausgeschimmelt, and therefore we should flash the display so the operator doesn't get misled by what's on the display. And that's also used when we're in battery test mode. I'd mentioned before that the battery voltage is tapped off and brought up if you're in the selector switch position that's measuring the battery, and that's combined with, let's see, where does it go? It makes its way around here somewhere. Yeah, here we go. It comes into this other input in the gate, and that also causes the lamp test mode to be turned on, thereby flashing the display. So if you're measuring the battery, let's say you have the input leads to the meter connected to something that you're testing, but you say, gee, I wonder how my battery's doing, so you temporarily flick the front switch, you rotate it over to the battery test position, and now the meter is measuring the battery voltage instead of what's on the test leads, and they don't want you to forget that you're in the battery test mode and think that that's the voltage you're measuring instead of the battery voltage. So whenever you're in the battery test mode, it turns on that lamp test feature, which makes the display flash, and that's just an indication to the user that, hey, this is the battery voltage you're measuring, not the voltage that's connected to the test leads. So that's a little subtlety of the operation. Well, we got through it, I think. This big honking schematic, I think I've explained everything of significance on it. And if you're a person that's stuck with it, that probably means that you're somebody who finds this stuff interesting. And if you were bored silly by it, then you wouldn't have got to this point where I'm talking about it. So hopefully you find it of value and it was worth my time describing it to you.